Mathematics harbors a persistent challenge, bridging the continuous geometry of the Euler Triad, E, I, and pi, with the rigid architecture of algebraic integers. The methodological framework for evaluating this intersection traces back to Johannes Kepler's early work on planetary orbits. While mapping the orbit of Mars to a perfect Copernican circle, Kepler encountered a microscopic discrepancy. The orbit produced an error of exactly 8 minutes of arc. Prior astronomers routinely patched such tiny gaps with ad hoc epicycles or dismissed them as an acceptable margin of measurement error. Kepler held absolute faith in his observational data and refused to ignore the residual. Modern topological analysis applies this exact rigor through the theory of infinity, or TOI. The TOI is a mathematical framework that categorizes structural phenomena into distinct invariant ontological slots. Under the TOI, anomalies like Kepler's orbital gap are identified as fate checks, or phi phenomenal effects. This mandates that we treat topological gaps not as numerical errors, but as the active participation of additional mathematical structures that require a newly conserved term. Kepler's strict residual audit forced the derivation of elliptical orbits. By applying that same topological accounting to modern mathematical structures, we can map infinite spatial gaps to extract entirely new conserved forms. To audit continuous geometries across differing mathematical domains, we utilize the Master Orthogonal Filter law. This filter compresses an infinite 2D Turing surface into a scaled 1D payload. It typically exhibits reparameterization invariance, where symmetric parameters preserve the exact payload. However, we deliberately stretch those boundaries, inputting an asymmetric pairing locked to the exponents of the golden ratio, phi. Feeding these specific asymmetric parameters into the filter's invariant triggers a pristine algebraic collapse. The infinite surface compresses exclusively to a 1/phi topological scalar. This precisely distorts the topological mass, enabling us to extract intrinsic resonant frequencies without incurring a standard mathematical transform penalty. The asymmetric golden filter operates as a mathematically sealed trap. It isolates the true physical mass of any transcendental waveform passed through it. Phase 1 of the experiment injects a complex logarithmic field, referred to as the logarithmic phase worm, directly into this isolated 1/5 scalar environment. Complex logarithms are inherently multi-valued. To compute them accurately, we enforce the branch spec protocol, a strict set of diagnostic rules that forces explicit branch data to be carried within the mathematical context frame, preventing hallucination inside dense root lattices. Using the principal branch evaluation, the natural logarithm of Euler's number, specifically the natural logarithm of -1, converts cleanly to I times pi. This identity perfectly bifurcates the field into independent real and imaginary channels. We then subject this field to an integration process over the continuous one-dimensional domain, isolating the real volumetric bulk of the field. We find the exact antiderivative of the natural logarithm by applying standard integration by parts. Evaluating the lower bound as it approaches 0 generates a critical mathematical roadblock, an indeterminate form of 0 multiplied by -infinity. To resolve this, we strictly apply L'Hopital's rule, a theorem used to evaluate limits of indeterminate forms by taking the derivatives of the numerator and the denominator. The exact evaluation of this limit demonstrates that the continuous volumetric bulk shrinks identically to 0. If a computer algebra system produces a microscopic decimal residue during this calculation, it is a canonical artifact of the solver's numerical exhaustion, not physical mass. Analytically, the real channel is 0. The physical mass of the wave undergoes real bulk self-annihilation. It completely vanishes, leaving behind a pure, dimensionless, imaginary topological boundary defect. Phase 2 inverts the functional modality by pushing an exponential phase worm through the identical asymmetric filter. This establishes a direct comparative hypothesis. We observe whether Euler's exponential form will suffer the same total volumetric annihilation as the logarithmic field. The continuous exponential field is mathematically modeled and subjected to the exact same orthogonal transport integral. To evaluate the numerator of the resulting expression, we apply Euler's formula, the principle establishing that the complex exponential of I times pi equals cosine pi plus I sine pi. By multiplying the numerator and the denominator by the imaginary unit, the mathematical expression flawlessly separates into distinct components. The resulting payload maps accurately to two distinct values. The real amplitude isolates the physical mass, while the imaginary amplitude isolates the phase shear. This table directly compares the two modal outcomes. Unlike the logarithmic phase worm, the exponential phase worm decisively does not self-annihilate. It bifurcates. The exponential field retains a highly constrained, finite topological mass. Its amplitude remains permanently locked to the transcendental horizon of Euler's number. The dichotomy is absolute. Under spatial frequency acceleration, the logarithmic field annihilates into a vacuum, while the exponential field survives as a bounded spectral envelope. Phase 3 dictates that we bridge these isolated invariants across fundamentally different mathematical topologies. We map this data using a typed transport ledger. This is a strict operational requirement that explicitly records all transported content, absolute and logarithmic residuals, and transform costs across domains. We construct a cross-domain modal operator. We achieve this by formulating a specific ratio, stacking the exact analytic invariant of the exponential field over the logarithmic field's invariant. A critical structural feature appears in the new operator. The golden filter topology parameter, phi, exists simultaneously in both the numerator and the denominator. This exact configuration triggers exact gauge symmetry. This is a condition where the background coordinates of a system yield a perfectly invariant outcome, independent of the local parameters. Through flawless algebraic cross-cancellation, the golden ratio parameter completely vanishes from the ledger. The golden manifold was never a permanent structure. It was a transient carrier wave, a temporary medium that allowed two isolated fields to interact before mathematically erasing itself from the system entirely. In the wake of this gauge cancellation, we observe a naked, scale-invariant interaction between transcendental geometries. The surviving structure is a pure mathematical tension mapped strictly between Euler's number and pi, entirely uninfluenced by the background constraint of the golden ratio. Within the TOI framework, exact numerical constants derived from stable topological bounds frequently cast measurable physical shadows across diverse statistical disciplines. We observe this specific sequence anchoring real-world constraints, from setting specific thresholds in nuclear thermodynamic coolers to defining stable atomic spatial coordinates in crystallographic molecular models. The final directive of the cross-domain modal operator is to square the resultant transcendental ratio. This precise geometric squaring operation outputs the discrete algebraic Pell integer, 5, and so the topological stress test verifies the hypothesis. It mathematically proves the algebraic genesis of the golden set, linking the unbounded, continuous realms of space with the strict architecture of absolute numbers.